of entities because that's the topic of this session. The first speaker is Vincent, and now just my phone went off, so I don't know the title of his talk anymore. You have the slides, and I can reach off there. Yeah, so the first slide, you can just take it away by yourself. So Vincent is the first speaker. Please welcome him.
Hello. Okay, thank you everyone. Thank you everyone for joining. I'm Vincent. In this talk, I want to talk about how to multiply polynomials when we do not have powerful multiplication instructions on the target platforms. This is a joint work with Yongbok Kim and Sochun Song. For polynomial multiplications, there are typically two cases we want to focus on in practice. The first case is the entity-friendly ring case, which in this paper, we're going to focus on the prime modulo case. The second case is the entity-unfriendly ring case. For example, where if we want to multiply polynomials over a ring modulo power of 2. In the second case, there are typically several approaches. For example, we can apply multiple entities and apply CRT to recover the coefficients in the desired coefficient rings. Or we can apply entity over large entity-friendly rings. In this paper, we focus on the third approach to apply something like addition-only entities, gradually transforming the polynomial rings into smaller ones entirely with additions over the ring without multiplications. For the first case, we study how to we generalize Barrow multiplication and show that our generalization enables suitable mapping to the cases where we have expensive long or high multiplications. As for the second case, entity-unfriendly ring case, we propose to apply Nussbaumer and revise the cost analysis with suitable cost metrics. For the target platform, we optimize dilithium on Cortex-M3. Dilithium is a NIST post-quantum cryptography standard. And in dilithium, we have something like, we typically compute several things, the polynomials over the coefficient ring modulo the prime modulus Q, modulo prime modulus 2 to the 23 minus 2 to the 13 plus 1. As for our optimization platform, we target the microcontroller Cortex-M3. The Cortex-M3 is a microcontroller with input-dependent multiplication instructions, with input-dependent long multiplication instructions. Since the long multiplication instructions are a variable time, we cannot use it to compute secret data. Therefore, a typical approach is to try to compute the long product with software emulation through low multiplications and try to accumulate the partial products with additions and logical operations for positioning the bits. There are two parts. First part, I'll focus on the entity-friendly prime case. I'll refresh the audience a little bit on multiplication instructions. But suppose we have all the elements, suppose we have integers in each of the 32-bit registers. So each of the rectangle represents a 32-bit register. And suppose on the left-hand side, we have A, an integer on leftmost rectangles, and B on the second leftmost rectangle. A long multiplication grabs these two elements and computes the 64-bit full-size product and stores the 64-bit full-size product into two registers. From the long product, we have two other multiplication instructions. The second one is a low multiplication instruction, which computes the lower 32-bit of the long product. Similarly, the high multiplication instruction computes the upper 32 bits of the long product. Now, on a Cortex-M3 platform, we can't really use the long multiplication instructions. So what do we do if we still want to compute the long product in the 32-bit architecture? A typical approach is to split all the operands, A and B, into two 16-bit chunks. So on the last row, I color the part with the actual elements, with the actual elements that are relevant to that depend from the source operands. So on the last row, we basically compute 4 partial products, compute 4 32-bit partial products with 4 low multiplications, and then position the low products at the correct positions and accumulate the results. And this not only amounts to 4 times more multiplication instructions, but it also amounts to several logical and addition instructions. To implement, for modular multiplications, there are generally several lines of approach. A very common approach is to multiply the 4 product, compute the long product, and then apply a special kind of modular reductions, whether it could be a Montgomery reduction or specialized reduction tuned for the target modulus. Bare multiplication, however, proceeds the entire procedure quite differently. In principle, it tries to compute a reasonably accurate Q multiple and subtract the Q multiple from the long product and hope that the high part of the long product are equal. And if they're equal, we can skip the high computation. We can skip the computation of the higher bits. So I put a formula over there on basically the definition of modular multiplications. So as we can move on further definition, we find that AB modular Q is basically defined as AB minus the rounded of AB over Q times Q. The target is trying to approximate the Q multiple reasonably accurate. So in bare multiplication, concretely, we replace the rounded part with another rounding computation, but this time modular a power of 2. In this case, I denote it as R. And then we can try to argue how far the rounded fractions are, and from this and from the distance from the desired one, we can then compute how close the modular results are. And in this work, we propose to generalize. To relax the conditions on the fraction part and show that this generalization can be suitably mapped to multi-limb arithmetic with software emulations. So here are the graphics for the general ideas, and in fact also the one we actually use in assembly. So for the first case, for the original case, we compute 4 products and add 0 over 2 for implemented rounding. Sum of 5 of the things, compute the 64-bit thing, and then extract the upper 32-bit products. Our generalization is to basically throw away anything that relates to the lower parts. So when we skip all the computation on lower parts, we basically only need to add 3 parts, and we also skip the carry computations. The result is deviate from the original one a little bit, but in general, it's still fine for practical applications in our context. Here's a little bit of math. I'm not going to dive into the details, but here are basically the important formulas and definitions, and you can try to find all the details and all the rigorous justifications in the paper. These are results of module modifications. So for the plain modification, the first row refers to the performance of the native by variable time long modification instruction. And the second two constant time long modifications, they are like software emulations through low modification instructions. As you can see here that the software emulation incurs large overhead. And as a reference, the low modification here amounts to 1 cycle and 2 cycle for the accumulated variant. So there are indeed a huge overhead if we really go for the software emulation approach. Such differences immediately translate into the supremacy of our generalized bare multiplication with approximation. So our generalization outperforms the prior module multiplication on platform, which is Montgomery multiplication, by a factor of 1.92. After as for the variable time computation for the signature verifications, we also improve the overall performance as the variable time long multiplication is a bit kind of slow. After improving the module multiplications, the overall improvement of entity is straightforwardly improved. So for the constant time computation, we improve the performance by a factor of 1.38 to 1.51, and also the variable time entity. After plugging the optimized entities, we also improve the core polynomial arithmetic metric vector multiplications on dilithium. Addition to the entities, we also plug in the optimizations to the accumulation of the polynomial products and obtain further improvements for the matrix vector computations. On the second part, I want to talk about how to deal with the entity-unfriendly ring case. In particular, the case where we have a coefficient ring that is modular power of 2. Cooley-Tukey FFT is like arguably the most commonly seen FFT approach. I don't think I have much time to go into the details, but to single out the differences in the approach that we propose, which is Nussbaumer, I'll briefly go over the conditions and the overall complexities and what they rely on. For Cooley entity, it asks the coefficient ring to be an entity-unfriendly one that containing the inverse of n, apply a bunch of multiplications, and transform the polynomial ring into n copies of coefficient ring. During the transformation, a little bit more concrete analysis, we need order n log n multiplications and order n log n additions. As for Nussbaumer, it doesn't really ask the coefficient ring to be an entity-friendly one. As long as we have the inverse of n, we basically apply a bunch of additions, transform the polynomial ring well into larger number of copies of coefficient rings, but during the process, we only need additions. Concretely, we need order n log n additions. In practice, we usually do not transform the polynomial rings into the smaller ones, and instead we usually stop earlier. So suppose, but this stopping criterion is usually platform dependent. Now suppose we have suppose we stop earlier once the dimension is less than or equal to t and switch to an asymptotically slower but concretely faster approach and try to revise the actual cost analysis of the Cooley-Tukey and Nussbaumer approaches. So after some analysis, we find that if we want to apply both approaches to polynomial locations, then the dominating term actually is a bit different by a certain platform-dependent constant. Now, another critical thing that we should focus on on our platform is the conditions on the coefficient ring R. And I'll explain a little bit how this difference make actual difference concretely. So for the power of 2 case, we cannot really define a large dimensional entities. Well, for modality, we can define a size 2 ones, but those are not very useful. And a typical approach is to try to apply multiple entities. And if we apply multiple entities, then we need to multiply the cost analysis by a certain platform-dependent constant. Other approaches, the large entity-friendly approach also amounts to multiplying the cost with a reasonably large constants. So on our platform, CoreM3, those constants are more like 23 if we apply 32-bit Montgomery multiplication, 12 if we apply our generalization or Bayer multiplication, and 6 to 9 if we apply multiple 16-bit entity, multiple 16-bit entity approaches. Now, what about Nussbaumer? Well, in Nussbaumer, basically the cost is already entirely reflected on the cost analysis on the coefficient ring operations. And since multiplications in modular power of 2 is super fast and our platform only amounts to a cycle, the overall cost is basically the same as the cost analysis for coefficient ring operations. Additionally, there's a technique I don't have time to talk about, which is Topic metric vector product. If you want to know how it works and why it actually applies to the delisting case, you can check the paper for details. There's the overall performance of the entities of the entities with 32-bit precisions. So on the leftmost column, we improve the performance of some of the transformations at the expense of at the expense of a bit more expensive multiplication phase. But overall, if we apply the idea to polynomial multiplications, then it indeed improves the performance. The performance of entities and also the performance of the entity-unfriendly case, both of them together translate into the improvement of the overall performance shown on the slide. In addition to delisting on CoreM3, we also apply the ideas to Saber, which is another lattice-based crypto system, but entirely operate over modular power of 2. We also apply the ideas to ABAVR, which is more like a legacy line of microcontrollers. On an ABAVR, we only have AB native multiplication instructions. So unfortunately, we need to emulate basically every ring arithmetic. And our generalized Bayer multiplication obviously performs the fastest on ABAVR compared to other entities, compared to other modular multiplication approaches. And as for Saber, we obtain a slightly different result than the CoreM3 case due to some precision issues. To summarize a bit, for the anti-prime case, we propose to generalize Bayer multiplication suitable for multi-precision arithmetic. As for the power of 2 case, we propose to apply Nussbaumer over the coefficient ring. You can check out the paper for more details and also the artifact if you want to try out how it actually works. Thank you for listening.
Yeah, thank you for your talk. Are there questions in the audience? The first question of the day somewhere? There are microphones in the alleys, I see.
morning, everyone. Thanks for the talk. I'm interested to know, because the Kulituki is well known for many hardware implementation as well as the software parallelization. So how about Newsbummer? Does it offer the same chance for parallelization in hardware and maybe like GPU stuff, or things like that?
Yes, thank you for your question. So a microcontroller is more like a single issue processor. So basically, optimizing through the cycle count very often translate to overall performance improvement. But for other processors or even like GPUs, which is like a hardly parallelized platform, one usually have to take memory consumptions and the memory access patterns into account. So for those cases, well, if you're already pretty sure that memory is fast in general, then maybe the approach translates to those platforms. But I think that might worth further investigation because the memory usage of Kulituki and Nussbaumer are actually quite different. Here. So after transformation, the memory usage of Kulituki NTT is basically the same as an input. It's basically the same as an input, but for Nussbaumer, we really have an roughly log n many elements we need to handle. Although in practice we stop earlier depending on platform, but this log n factor is roughly something grow with the problem size. So this one will be something we really need to take care of, how to handle the log n factor from the memory perspective.
Okay, thank you.
I think we would have time for one more question if there's another question. Maybe just a quick one from me. Is there any intuition to know whether Barrett or Montgomery is better on a given platform?
Yes. So if we have extremely powerful long multiplications, then one should really go for Montgomery multiplication or an approach I haven't talked about, like Plantar multiplication. I think the next talk will focus a little bit more on that approaches. So if we have fast multiplication instructions, go for Montgomery and Plantar. But if we have if we have slow long multiplications, possibly due to multi-limb emulation, then in this case, definitely go for Barrett multiplications.
All right. Any other question? I hope not. We are tight on time. Okay, let's thank the speaker again. Then we are going right over to the next talk. There's no time to waste. There's coffee waiting at the end of the session. So let's welcome the next speaker, Jipong. Please take it right away. Can we have the slides, please? Thanks.
It's my pleasure to present this work. My software implementation of Shark, Kyber, and Delicium on RISC-V. This is the outline for the next 20 minutes. First, motivations. So why did we undertake this work? We identified 3 motivations. Yeah. The first, although optimized implementations of PQC on ARM platforms have received significant attention, however, that on RISC-V is limited. The second, hardware implementations rely on the C reference implementation as their baseline. So we think using the fully optimized software implementation as their baseline would be more reasonable. Yeah. The third, we found that optimizing PQC for different RISC-V present a unique challenge due to the modularity of RISC-V. Yeah. Here we're using symbol to present 8 different RISC-V ISA combinations. Yeah. These are not just theoretical combinations. Yeah, they represent the commercially available cores as listed here. Yeah. And then background. This is the basic introduction to RISC-V ISA. Here, I represent base integer ISA, and M, multiplication and division, and also B extension, V extension. Yeah, we often use G to stand for a collection of several extensions. And then the FIPS 202, 203, and 204. Yeah, the first established the SHA-3 standards. The core component of SHA-3 is the Kashak F1600 algorithm. The last two, MLKM and MLDSA, based on Cabal DELISM respectively. The time-consuming operations in them is SHA-3 and entity polynomial multiplication. The Kashak F1600 algorithm operates on a 1600-bit states and consisting of 24 rounds, with each round including 5 steps. This is the algorithm of one round. We can see that all of the calculations mainly involves logical instructions. For example, XOR, rotation, note, and. The common optimization techniques for Kashak include bit interleaving, line complementing, and in-place implementation. The last one is lazy rotations. It is only used for the ARM platform. There are several common optimization techniques for NTT. Yeah, for example, the algorithmic or implementation level optimization of modular multiplication algorithms. For example, the Montgomery method, Barrett method, and the recent Planter method. The second, a layer merging strategy is used to reduce the memory access. And then parallelized implementation using SIMD or RISC-V vector. This is the targeted platform in this work. It supports the both 32-bit and 64-bit execution states and support the GC-BV ISA combinations. Yeah. Regarding the V extension, the vector length is 128-bit, something similar with the ARM new. Regarding the microarchitecture, it supports the dual issue of scalar instruction and single issue vector instructions. The CPU manufacturer did not provide the information of the instruction latency and the CPI. Yeah, the CPI means cycles per instruction. So we performed a large number of benchmarks regarding this call to obtain this table. Yeah. We can see that for simple integer instructions, the latency is 1 and the CPI is 1/2. We can also see the two instructions provided by the B extension. Yeah, it's similar. Latency is 1 and CPI is 1/2. Yeah, this table will be helpful for optimizing Kashak and NTT on this call. And then the optimized Kashak implementation. Let us start with how to optimize Kashak using 64-bit RISC-V, using I and IB ISA combinations. For the IV64I, the first thing is how to implement the rotation operation. Yeah, we need 3 instructions to implement it. Yeah, But with the support of B extension, yeah, one instruction is enough for performing the rotation operation. Regarding the link complementing, we found that for the version of IV64I, this technique can reduce the number of node operation, so it's useful. But with the support of B extension, we have an instruction end-to-end, which can perform the node operation without additional cost. So we don't use this technique to this version. Regarding the in-place implementation, we use the existing method. And then we performed optimization regarding the future of the microarchitecture dual issue to reduce the RAW hearts, yeah, to improve the pipeline efficiency. The RAW means read after write, yeah. And then the Kashak on 32-bit RISC-V, yeah. The first thing is to determine which techniques is beneficial. And then we found that the biggest challenge is we don't have enough registers to accommodate the 1600-bit states. So we designed an allocation strategy to use 20 registers to keep some state resident in the registers. Yeah. The left side is the previous implementation. We can see that the line 2 and line 3 read data from memory, and line 4 will use them. So the line 4 will wait for a while to until the date is ready from memory. The right side is our implementation. Now we can see the data read from line 1 and line 2 will not be used until line 7 and 8, so to reduce the RAW hearts. So our implementation will be more pipeline efficient. And then Kashak using RISC-V vector. The implementation is nearly identical to that on IV64I. And because the vector length is 128 bits, so it's a two-way implementation. And the CPI of this core, the CPI of the vector logical instruction on this core is 2, so the speed of the IVV version will be slower than the scalar version. Yeah. Hybrid idea is an interesting approach to mix this scalar code and the vector code together to improve the efficiency. Let us see two instruction sequences. Yeah. The first, 2 vector AND consumes 4 cycles. Yeah, and then 2 vector AND followed by 4 scalar AND also consumes 4 cycles. Yeah, it's interesting. One reason is that the vector logical instruction has a very long latency. Yeah. And a precondition of hybrid idea is that the scalar and the vector units of this core have independent execution backends. And then we try to construct the hybrid implementation using IV64I plus vector version. But we found no performance improvement because the scalar version is fast enough. And then we construct the hybrid implementation using 32-bit plus the vector version. Yeah. One is 32-bit version and one is a vector version. So we get the hybrid 3-way implementation. Yeah. We found it's faster than both scalar and vector implementation. This is the Kachak result of 4 scalar implementations. Yeah, in short, our implementations are faster than previous works than the reference works. It's a hybrid implementation. Yeah, it's also faster than the vector version than the scalar version. And then optimized entity implementations. The Cabra uses the 16-bit entity, and the Delism uses 32-bit entity. And the plantered multiplication is a recent method. Previous work has shown that it will faster than Montgomery method on CHES M4 and RISC-V. The left side is the plantered multiplication. We can see 2 of the 4 instructions are multiplication. Yeah. The right side is Montgomery multiplication. 3 of the 4 instructions are multiplications. Yeah, you know, the multiplications instruction is more expensive than shift, than add or sub. So here, the plantered method will be faster. So we will prioritize the plantered multiplication. For the scenarios, the plantered can be used, so we will use plantered. For others, we will use Montgomery method. And then, this work does not provide any novel techniques to improve NTT, but we found that to optimizing the pipeline efficiency will significantly improve the performance of NTT. Let us see a suboptimal case. Yeah. This instruction sequence computes the plantered multiplication. We can see each instruction depends on the result of previous instruction. So it's RAW hard. Yeah. So we try to interleave several independent sequences together to improve the pipeline efficiency. So we can achieve at most 4-way interleaving. Yeah. And for the cost of the Cabra entity, the cost is reduced by more than half. This is the result of NTT, Cabra entity, and the Delism entity. Yeah, our implementations are faster than previous works, than the reference works. And then, after integrating the optimized Kachak and the optimized entity into Cabra and into Delism, we obtain this table with a lot of data. In short, our implementations are faster. And conclusion, we provide Kachak and NTT optimized implementations for various RISC-V, hoping to be helpful to the community. This is a link to our artifact, and part of the implementation has been adopted by a public crypto library. And please refer to the main branch for the latest updates. That's all.
Yeah, thank you for your talk. Are there questions in the audience? Please use the microphones in the aisles. Is it a question or an escape? An escape, okay. So maybe let me ask the first question then. It looked like some of your optimizations actually require more instructions that are scheduled more efficiently. So how do your optimizations affect code size?
I'm sorry, I didn't catch that.
Especially for Kachak, it looked like you are issuing more instructions in a short amount of time. So how does the code size get affected by your optimizations?
I'm sorry.
does your program code get longer or shorter?
Mhm. The code size is bigger.
By what factor? How much?
Yeah, we use the assembly language to implement it. So the question is whether the code size will be bigger.
Yeah, and by how much?
Okay, thank you. Yes, it will be. But we can see regarding the Kashak implementation, we use a technique named in-place implementation. So which means that we will implement using assembly language to implement one round, and then warp it using a for loop. Yeah, so to minimize the code size, so it will not become bigger and bigger.
Okay,
Yeah.
so since you don't unroll the loops, it's still not a big increment in code
Yeah.
size. Okay, thank you. Any other question? Is the code online?
Yeah, the code, yeah. There is a link to our artifact, yeah. Yeah, you can see the main branch for the latest updates. Yeah, we are updating it.
Okay, if there are no more questions, then let's thank the speaker again. And then I'm trusting that the third speaker has arrived as well. Very good. So the last talk of this session that departs us from the coffee is going to be given by Chunming. So please take it away. Welcome.
Okay, thank you so much for the introduction, and good morning, everyone. My name is Junming. I'm glad to have this chance to talk about the new work on the topic, a new trick for polynomial multiplication, a verified CRT polymorph utilizing a monomial factor in collaboration with Bo Yao and Bo Ying. Before we begin, I want to quickly go over the list of our contributions and at the same time give a rough outline of the structure of today's talk. So we first introduced the practical use of CRT with monomial factors. When combined with standard entity-based polymorph, this allows us to compute polynomial products modulo this weird-looking polynomial form. We will see in a few minutes why this can be useful. The second contribution is we described a way to align the zeros in the goods entity, the zero paddings in good entity, so that we can perform zero skipping efficiently while avoiding code size issues. We will cover the first two techniques in the first two sections of this talk. And lastly, we combined both ideas and implemented them in a neon-based polynomial multiplier targeted for n-true prime. And we actually achieved state-of-the-art achievement in the end. We made the code publicly available in a GitHub repo shown here. There are some other contributions we made that we couldn't really fit into this talk. These include some other optimization tricks for entity and modular arithmetic in general, and also our verification of our code with the CryptoLine toolkit. So we can start by talking about what we are trying to achieve with a CRT with monomial factor idea, which is to combat this recurring problem in entity-based polymorph. Consider this scenario where we want to multiply two polynomials, each with 500 coefficients. That is, their degree is at most 499. The standard approach is to use x to the 1024 minus 1 as the new redundant modulus and uses the celebrated radix 2 NTT to perform multiplication in this quotient ring very efficiently. This is all fine and good, but things become tricky if the length is increased to 520. Now the same choice, n equals 1024, doesn't work anymore, and we have to find another bigger sufficient n. In many cases, this will be a lot much bigger because of both the smoothness requirement on the NTT side and the existence of the appropriate principal root of unity. So we see that in many cases, a small deficiency on the degree of the modulus is the only thing that stops us from using some easy and efficient modulus x to n minus 1. As it turned out, this problem gets even worse when we are considering NTT unfriendly coefficient ring. For the case of entropy prime, this is true for pretty much all of the parameter sets. So this includes the S entropy 761. The first requirement is that we need degree Q to be at least 1521. Second, because we want to use vector instructions, the common practice is to use incomplete NTT with size 16 base case. So this will require that n over 16 to be an integer, and it should divide into 4590. For the NTT to be as fast as possible, we want to only use radix 235, so the small radixes. All of this considered, we can see that this makes our options very limited. The smallest one is to choose the NTT size to be 175. This corresponds to n being 2160, which is a big overkill. Highlighted here is the choice to use 90 NTT and n equals 1440, which is slightly smaller than the requirement. As a quick side note, I want to mention that the state-of-the-art approach actually embraces the use of radix 17. Specifically, they propose to implement radix 17 with truncated radar NTT. It is much simpler and much faster than the naive implementation, and the math behind it is quite elegant indeed. However, at the end of the day, it still uses quite a bit of multiplication, so we still want to avoid it as much as possible. So this is where our trick comes in. It is based on the observation that x to n minus 1 and x to the n prime is guaranteed to be coprime. So CRT gives us an easy way to multiply modulo their product, as long as we know how to multiply modulo each of the factor. We will call the two subtasks as the main part multiplication and low power multiplication respectively. So this allows us to pick n to be any convenient value and set the n prime to be the remaining deficit. So in our case, we can pick n equals the highlighted 1440 and the n prime to be the remaining 81. As we can see, this is quite a versatile technique, and we believe that this can open up a lot of brand new designs even in other application settings. To analyze the cost of this CRT mapping, we can first see the forward direction, which is frankly quite trivial. More concretely, in the main part, we only need to perform zero padding, and for the low part, we can just do truncation and preserve only the first n prime coefficient. The inverse direction is also quite cheap. As we can see from the pseudocode or the figure on its left, you can see that it only requires n prime subtraction. It is remarkably simple. Due to how cheap and simple this is, and how small n prime is compared to n, we can expect that the full-length polynomial multiplication to be basically as fast as the main part multiplication. Which brings us to the next section, aligned zero skipping in goods entity. Because of time constraints, I can't really go into the detail of how goods entity works in theory, but only show how it is implemented in practice. So we first split the 1440 coefficients into 90 chunks. So each of AI is a polynomial of length 16, and they together satisfy this equation here. And we insert the 90 chunks into a 10 by 9 array along the diagonals. So as we can see from the red arrow. And the last thing we need to do is to perform 2D entity, so 10 entity in the vertical direction and 9 entity in the horizontal. During the order is unimportant, and we choose to do the vertical direction 10 entity first, so we will refer to it as the layer 1. Because of the zero padding in the forward direction, in layer 1, there will be roughly half of the chunks to be 0. This suggests the use of zero skipping to greatly simplify the 10 entity for each column. Similar techniques have already been proposed and used in multiple prior works. But all of them faces the same issues, which is because of the differently located zeros in each of the columns, we will need multiple dedicated design just for each of the cases. So in our case here, it is 9 designs. And depending on the specific goods entity dimension and the characteristic of the computation platform, this increase in code size can be prohibitive. To address this, we propose to simply cyclically shift each of the inputs, the 10 inputs within each column, so that the zeros are aligned in a neat manner. So in the end, we will need 2 designs only. That is, one for the 4-0 case and one for the 5-0 case. Due to the time shifting property of the discrete Fourier transform that translate also works in NTT, we know that the output will be twisted, so they are multiplied with a twisting factor, and this can be undone easily with some post-processing modular multiplication. Some might be worrying that the extra added barrier multiplication might be very costly, and so that this whole stream might not be worth it in the end. But we can notice that at the end of 10 NTT, because the size is so close to being overflowing, we naturally need to put a barrier reduction here anyway. So since we're replacing it with barrier multiplication, the extra added cost is only moderate. In fact, since we put a lot of effort into making sure the zeros are in strategic places, so that the 10 entities are simplified most effectively, we actually observe a much faster implementation compared to, say, not performing zero skipping at all. So this is definitely worth it. To see how much we're actually saving from the zero skipping, we can see the following demonstration. So the intra-column 10 entity are itself also implemented by a goods entity, in this case 5 by 2. So they are also rearranged diagonally into a 5 by 2 array. And we will focus on the left column, which needs its own 5 entity on the right. We will call the 10 inputs to the 10 entity, F0 to F9, and the 5 entity by G0 to G4. Now, when we know F3 to F6 are all 0, we can see that this translates into G1 and G4 will be also 0 in the 5 entity part. So by truncating the computational flow graph appropriately, we see that we actually save a lot of addition and subtraction and effect one entire modular multiplication entirely. So we think it is quite a substantial saving for NTT implementation. Now we can take a look at the performance matrix of our implementation. First, we'll look at the full-length multiplication compared to the full-length multiplication, including the reduction by x to the 761 minus x minus 1 with the previous state of the art. The first thing to notice is that we actually use much fewer instructions overall. So as a baseline, we can already expect a roughly 1.2x speed up, assuming the IPC is roughly the same. So instruction per cycle is more or less the same. This is roughly what we observe in the Cortex A72 platform. Moreover, since we actually use a lot less multiplication instruction, we see that in some platforms, namely A43 and A76, the IPC is actually much better. So the speed up is actually even more impressive in these two platforms. Next, we will take a look at the subroutine performance. One interesting comparison is you can see that the low part multiplication actually used less than 1/10 of the cycle count compared to the main part multiplication. So this confirms our intuition that the multiplication is basically as fast as the main part multiplication, and the low part can be considered practically free. Next, to see how effective the line zero skipping trick is, we can compare the layer one entity of the main part in both the forward direction and the inverse direction. Here we don't see a substantial difference between them, but one important thing to note is that in the inverse direction, we actually never reduce the output range. This task is deferred into the next subroutine. Reducing all the outputs needs around a few hundred cycles. So if we take this back into account, we see that aligned zero skipping is actually quite effective. To summarize, we first introduced the use of CRT with monomial factors, and that allows us to use extensively the S to N minus 1 and overcoming the requirement on decree of Q. The aligned zero skipping trick makes the first layer in a goods entity much faster, while the code size can be kept as small as possible. Finally, we didn't go into this, but we actually formally verified the functional correctness of our implementation with the use of the CryptoLine toolkit. If you aren't too familiar with this toolkit, I recommend another talk in this afternoon that will be given by Ming Xian that will go over more detail about this toolkit and specifically the algebraic linear analysis engine that is newly added and which we also use extensively in our verification. Thank you so much for your attention.
Yeah, thank you for your talk. I have other questions in the audience. Yeah, can you please take the microphone in the aisle?
So first, thanks for the talk, really well given, really nice to hear. Are there any, like, I definitely occasionally get the thing like, okay, this is not a power of 2 polynomial size, but are there any current PQC algorithms or like immediate applications for like a wide range of things which require these techniques? Because it seems like this is really non-power of 2 polynomials,
Yes.
which I definitely occasionally have like, okay, non-power of 2, but they're always like in prototype things or, so do you have an immediate application for this?
One thing we're currently looking into is the application of this technique, the CRT with monomial technique, in the application of HQC, so the new crypto scheme. It uses we really want to use power of 2n or even 2 to the power of 2 to the power of some power of 2. So in one of the parameter set, this is just over one very convenient choice of n. So we're actually looking into the application in that instance. So yes, one of the parameter set of HQC scheme.
Have you looked at pleomorphic encryption? Because for some of the BGP-like schemes, there's some non-power of 2 where it would be nicer to use non-power of 2, but people keep changing the scheme to power of 2 because that's what all libraries are written for.
Sorry, I am not too familiar with fully homomorphic encryption, but as long as n is slightly larger than a power of 2 or some other convenient values, I think, yes, this technique is definitely worth a try. So we will need some future work to investigate further.
I think I'll definitely be able to use this. Thank you.
Thank you.
Any more questions? I think there's one more here.
Thank you for the talk. I want to know what are the differences between the align zero padding of goose trick with Kulu-Tuki with twisting. Because for me, they are kind of the same and just describing the different name.
So, yes, we actually wanted to put this into our slides, this observation. So we observed this similarity as well, but the first thing is that because of diagonal, so we are actually in the language of discrete Fourier transform, the vertical direction is actually dilated. So yes, it's very similar, but we know that we see that this is in backward direction because 9 is -1, so the inverse is also -1. But so when we dilate the signal by 9, we need the frequency space is also shrinked by it's also flipped, or it's also shrinked by -1. So this corresponds to this being in the inverse direction. If this isn't 9 by 10, on some other values, there will be skips from this. So the zeros will not be contiguous. But in Kulu-Tuki, it is always contiguous. Yeah, so this is kind of a coincidence here. Another thing is we use align zero skipping here, but since we do the twisting, so the inverse, in the inverse time, the whole design is still keep the same. So the inverse, we still enjoy the very clean, very simplified goods entity in the inverse time. We only need to slightly adjust the forward side. So.
Okay, I guess I'll try it out myself.
Yeah, definitely give it a try.
Any more questions in the audience? Then maybe I can ask one more before we have coffee. So your trick of pruning the entity,
Yes.
does this apply to all layers or only to certain layers?
Because of the intermixing of the coefficient that so that here, when after this butterfly, while this is 2, 0, the output will in general be all non-zero. So in the second layer, namely the horizontal direction, the 9 NTT, there will no longer be any zero. So we have to use the original full 9 NTT. So no zero, no pruning in the later layers.
Okay, thank you. Okay, if there's no more questions, then let's thank the speaker again, please. And then I would suggest that our last job for today, before we have the coffee, the first coffee of the day, is to thank all the speakers of this session again. Thank you. Now you might leave the room.